All right, how's it going, everybody? We are here for our second video of week two. I'm making this video on January 22nd here. We're going to talk a little bit of section 6.2 today, and we're going to look at computing some volumes today with integrals rather than computing some areas. It's definitely going to be the case that I think these are a little bit tougher than some of the things that we've seen before. It's not going to be too bad, but it's definitely going to be, I think, a little bit harder than just our difference between two areas that we looked at last video, for example. But the key here is that we're still going to be sticking it out, thinking in terms of Riemann objects. As long as we can imagine what object we are adding together, an infinite number of, to achieve a one higher dimensional object, then we're going to be able to set up all of our integrals just fine here today. And remember that I am loosely defining, this is sort of a little bit of a Tony definition here, unofficially defining a Riemann object to be any n-dimensional object of which we can add up an infinite number of adjacent copies. When I say copies, they're not necessarily all the same thing as each other, but they're all described the same way to create an n plus one dimensional object, right? So what we've been doing so far, and pretty much every single use of a Riemann object that you've done so far in your life, has been adding one-dimensional Riemann sticks to create two-dimensional areas, right? And when I say 1D Riemann stick, it's technically the case that we've been drawing these as rectangles all the time, but these are always rectangles that have some infinitely narrow width right there, right? So this is really not really a rectangle once we've applied our limiting process that's associated with the our definition of an integral, right? Our definition of an integral is the limit of a Riemann sum, where these rectangles get infinitely narrow to the point where they're really literally just a single vertical line. We know that lines don't have area, but what we're kind of defining our integral to say is that if you add up an infinite number of one-dimensional lines, you get a two-dimensional area. All we're going to do to extend that idea today is to say, now let's take a bunch of two-dimensional areas and add a bunch of them up to achieve a three-dimensional volume. I think that our most basic example, our analogy to this is that, you know, when you literally start learning about like dimensionality, and I mean, I don't know what like grade school level topic is this, like second, third, fourth, fifth grade or something like that, and like one of your first science classes, you talk about the difference between like two dimensions and three dimensions and stuff like that. And I think the like not technically correct but excellent visualization example is that we sort of think of like a piece of paper as being only two-dimensional. We think of paper as not really having any thickness, just length and width. We know that it technically does have some thickness, and kind of the reason I know that is because if you put a bunch of them together, it's got some volume to it, right? But the whole point is I could then take a stack of paper and now it's a volume of things. It can actually have height right there. So paper is not technically correct for this, but it's a good visualization. It is a sheet, and when you add together lots of sheets, you're going to end up with a volume rather than just a two-dimensional surface right there. So what we've been doing is we've been saying that area is really just length times width. That's exactly our rectangle association right here, and we can see it in our integral. This integral says this is literally an S for sum. This says add up a bunch of, and what is the? I guess this is more appropriate to call this like height times width right here, right? But whatever, I don't care. Length, width, height, those are all in a sense equivalent to me. Those are a matter of perspective, the difference between those things right there. So the bottom line is we've multiplied two length measurements together, and length times length gives us length squared. That's always going to be area right there. So remember that dx is a length. It's an infinitely short length, but it's still allowing us to grow into a second dimension. It's really important right there. So today what we're going to do is we're instead going to compute volume. So if we still want to perform this by computing an integral, we're still going to have a dx term which handles one of the three dimensions that we want to multiply together. So what's going to need to be the case then is that we have two dimensions represented within our integrand. So we're going to, instead of being integrating a height function, we're instead going to be integrating area functions. That will allow us to step up our area description to a volume description. Two-dimensional object, if we add together an infinite number of adjacent two-dimensional objects, we're going to get a three-dimensional object, right? So I hope that this kind of like comparison here is, a pretty reasonable analogy in my sense, and I think I'll kind of indicate this with some different notes right here. Area I can think of as being like meters squared, and dx as being like meters. Yeah, this is going to be giving us meters cubed. That's going to be our volume description right there. So area is a squared length. Dx is a one-dimensional length. The product of them is going to give us a three-dimensional measurement right there, which we call volume. And I would be crazy to suggest these things to you without also showing you what you guys should expect to experience when you're in Calc 3 next semester. Another way that we can think about this is rather than simply doing just area times length to get volume, we could instead think of volume as you somewhat probably more traditionally think about it. I mean, honestly, I don't think anybody would tell me that this is their formula for volume, area times height. I think if I were to just ask you, hey, what's the formula for volume? All of you would tell me it's length times width times height. Well, that's exactly what you're going to do when you're going to look at different ways to formulate volume statements when you're in Calc 3. You should obviously notice this requires a double integral right here, which is sort of opening a big can of worms, which is why that's part of its own separate class out there in Calc 3. But it's, I mean, Calc 3, the title of the course is Multivariable and Vector Calculus. Multivariable, you're looking at them right there, right? So multiple integrals going on. But this is really just the exact same thing right here. We're multiplying, and it's typically written as z is f of x, y right there. So this is really your x dimension length times your y dimension length times your z dimension length. That's going to get you your volumes. Hey, Kaislala there, how's it going? So this is what you're going to expect to see next semester, and it completely follows our intuition. We just now, in this case right here, have two of our dimensions being infinitely small times a third length. So this is just meters times meters times meters, gives us meters cubed, where only one of them actually has a measurable length right there. But this is what our route is going to be today. So all the integrals that we build today are essentially going to look like this. So all that means to me is today, our one job is to say, all right, how should we define the area function? If we can do that, then we've got the integral. We'll be able to perform the integration. We're good to go. The key to today is understanding that volume can be represented as area times height. Our height term is going to always be the dx or the dy, depending on how we choose to set up the integral. Our integrand should always be representing an area, a two-dimensional area, rather than a one-dimensional height, as we've previously seen in our integrals here. So we're going to do a handful of examples here today. I do want to point out to you, if you're looking above my head right here, that we're going to get some more volumes. This is not going to be our only day of discussing volume. We're going to have several sections that are going to give us alternate techniques for computing volumes. And as you're seeing right here, it's going to be another major topic in Calc 3 as well, as talking about volumes. But you're going to do it in Calc 3 a little bit differently with multiple integrals rather than just integrating different area formulations right there. So lots and lots of different things to say about this, and it'll be covered several sections in this class, several sections in Calc 3 next semester as well. So let's hit some examples here. And what I should say is this. In general, get out of here. What I like to always do with myself is say, when you're doing math and it starts getting hard and you see something that you're a little unsure about, an awesome thing to always do for yourself is always to prove something that you already know. Go and do something where you already know the answer to the question, so that by the time you get to the end, you can look at it and say, cool, I nailed it, rather than just be like, I don't know, I guess that's the answer. That's not a good place for you to kind of ever be in right there, all right? Another thing I'm going to say is Calc 1, I kind of think of as the end of easy math classes. From now on, everything is going to be pretty dang challenging, even if you're really good at math. And so it really matters that you stop and kind of do these grounding events to kind of make sure that you are confident in the thing that you just did. It's almost like a little bit of a feel-good experience. It's sort of like building this positive muscle memory right here. So we're going to come up with the volume of a sphere. This is sort of like a geometry fact that I feel like typically somewhere between a third and a half of my students know this, but I also think that you're just not going to be too terribly surprised when you see this, whether you know it or not. This is going to be a formula that you recognize. If you want, just Google volume of a sphere right now. You're going to see a pretty easy formula. It's obviously got pi in it. It's obviously got a radius term in it. We're going to go ahead and derive the formula for the volume of a sphere right now. So we need to think to ourselves, what's our sphere look like here, right? So let's draw ourselves a sphere and talk about how we can describe a cross-sectional area that we can use to accumulate the overall volume. So, tough circles today. That didn't look very good. So that's not just a circle, though. I'm going to try and describe actually a sphere, right? So we're looking at a whole sphere that's sitting really in a three-dimensional plane, right? So I guess another thing you should be imagining is an axis that's sticking straight out at you from the origin right there. Our z-axis right there. And when I'm thinking to myself, at least one thing that I see is really convenient. I kind of want to like remember back to the last video in section 6.1. A lot of the things that we looked at were saying things like, do you want to build horizontal Riemann sticks and accumulate them vertically? Or do you want to build vertical Riemann sticks and accumulate them horizontally? And there's some strategy decisions that are associated with that. There's good choices and there's bad choices right there that are going to be easier and harder for you. The obvious nice thing about a sphere is that all perspectives are the same. It doesn't matter if we think of this as dx, think of this as dy. If we try to accumulate sheets top down, sheets left to right, it's all going to be literally the exact same, just a change of name of variable that we're using to describe the axis that it's on. So I'm going to think of this as us accumulating some left to right circles here. So my Riemann object is like that circle right there. And I'm going to say my Riemann object is a circle. Right? That's going to be the area that we're going to accumulate an infinite number of those circles, and collectively they will produce the area of the overall sphere right there. So some other things I know. This location right there is at negative r, and this location right there is at positive r. It's a radius r sphere right there, so it just goes from negative r to r since I've centered it at the origin right here. And one of the things that I want to ask myself then is, what does this circle look like? Right? One of the important features that I'm seeing of this circle, I mean, what's the circle is sort of centered at that dot right there. That's the center of the circle, is sitting there on the x-axis right there. And what we know is that we want to find the area of the circle. Well, I need to just do like a pi r squared, right? But when I say r, I've already defined r to be the radius of the sphere. And what I can see is, because that Riemann, that representative Riemann object that I've drawn is not like perfectly centered at the center of the sphere. It's off to the side. So it should certainly be a smaller circle than the full like diameter of the sphere, like a great circle that's on the sphere right there, right? So I don't want to use the letter r. That's kind of all I'm trying to say to you right here. I've already defined r, and r is like the maximum possible radius of one of our circles. I've drawn one that's probably a little bit smaller than that. I want a more representative idea. So the thing that I'm seeing here is that if I want to talk about the radius of this circle right here, it seems to really just be whatever the y value is at that location. It's just the height as measured from the x-axis vertically up to the edge of our object right there. So I feel like I can say to myself that the area of our circle, our representative Riemann object, is pi y squared. One circle, one two-dimensional circle being sliced this way out of our sphere, is going to have that height of y as its radius on our graph right there. So pi y squared is my generic area of the circle. What we know is that that height y is going to change depending on which of the infinite number of Riemann circles that we're adding up here. It looks like as we get closer and closer to the x value being r, we should have very tiny values for y. And it looks like when r is 0 is when we'll have the maximum value of y. When x is 0, r and y should be the same value right there. We'll get the largest possible Riemann object right there. Right? So this is my generic descriptor of my area. But here's sort of the thing that I'm seeing now that's slightly my dilemma. If I'm going to add up circles, right, these vertical circles right here, sheets of them from left to right, what that means to me is that we are building a dx integral. That says from x value from negative r to positive r, add up the area of that circle. So I'm going to say, since I defined my Riemann object to be a vertical circle, that's a kind of weird description. I'm putting that in quotes because that's kind of a funny thing to say. We want to integrate over the x interval negative r to r. So it seems like what I want to be doing here is saying that our volume should be the integral from negative r to positive r of our area definition right here, dx. Those are x values, negative r to r. Technically, negative r to r could be y values, but I didn't draw my Riemann object that way. I based on the fact that I'm defining y to be the radius of my circle, that means that we're adding these circles from left to right. So all the x values from negative r to r, they all have their own circle, and we're adding up those infinite number of circles there. So it looks like we really want to state this as negative r to r of a y squared, or excuse me, I keep on writing a. That should be a pi y squared. So what you can see here is that our little bit of dilemma right now with our integral is I have a dx integral, but it's got y stuff on the inside. So now I feel like I need to relate x to y. I need to know what is the relationship between x and y in this scenario right here. And what I'm going to picture for myself now in here, and I'm going to draw a little bit of an extra part in here, is I'm going to picture for myself this right triangle right here. In this right triangle, this is that radius of y. Y is the radius of the circle. This distance right here is the radius of the sphere. It's actually r. And if I'm going to call this vertical height y to the edge of the sphere, then certainly this is the x value that's associated with it right there. So it certainly looks to me like x squared plus y squared equals r squared. I hope that's not a terribly surprising relationship for us to see with a sphere. And this is good because this is going to help me relate x and y to each other. It looks like for my integral over here, I want to solve this equation for y so that I can replace y. And in fact, actually, being a little bit smarter right here, it actually looks like I can do slightly less than that. I don't even actually have to solve this thing for y because I really just want to replace y squared. So actually my substitution there, I can do like one move less of work right there. So I think that I can now use this to help me rewrite my integral now. I now have related y to x so that I now have a way to have a dx integral with x's on the inside. So pi times r squared minus x squared dx. And now we're cruising. Now we can do the integration. We know that r is just a generic constant describing the radius of the sphere, so I'm fine with treating r like a constant, and I expect for there to be r's in my answers. I know that pi is just a constant, so I can bring that out front right away. And now we've got a pretty easy integral to do here. This is going to be x times r squared minus 1/3 x cubed. And we're going to evaluate this guy from x equals negative r to x equals positive r. And this pi is just sitting along outside for going along for the ride, just a constant multiple there, right? So let's go ahead and do our groupings here. Maybe I should give myself a little bit more room. It always takes a little space to do our evaluations here. So my volume statement is we should be getting pi times, and I'll just open a big old bracket here. Our first grouping should be r times r squared minus 1/3 r cubed minus negative r times r squared minus 1/3 negative r cubed. Okay. Let's do a little simplifying and see where we land. That's a negative r cubed times the negative is a positive. So what do I get in here? 2/3 r cubed from the first group. And then this will be a negative 2/3 r cubed inside the parentheses, but we're subtracting it. So it's going to be an additional plus 2/3 r cubed. And we're getting 4/3 pi r cubed. That's exactly the formula for the volume of a sphere right there. So hopefully that's really satisfying to you. I feel really good about some of these like simpler problems right here. And I know that even this wasn't super simple, right? Like, I mean, this was kind of weird right here that we had to stop and think about not just a sphere, but we had to think about building our own circles from those circles, relating the circle and the sphere with their lengths based on a right triangle over here. Like the Pythagorean theorem fell into this, the guy right here. It was sort of easy for me to build my integral, but with sort of like the wrong variables, right? But then doing a little bit more algebra and trigonometry right here, we're able to determine the more appropriate representation for our integral here, only in terms of x parts. And we did land back at our volume of a sphere, the known volume of a sphere, 4/3 pi r cubed right there. So pretty cool. I find that good. I hope that's the case right there, Room with Google Eyes. Uh, I think that our book is like really, really good, but every once in a while I'm like, man, you could have just put like one more paragraph in there and that would have been twice as good, and they don't. And so sometimes I feel a little bit lame when I just repeat book examples, but also sometimes I feel like there's value in actually like 100% understanding a book example rather than just being like, okay, I could mimic that, I think. There's value in getting some better depth on some of these guys right here. Other fun fact right here, by the way, I'd just like to point out. What's the derivative of volume? So, unrelated to today's topic, but a very, very important broad concept in calculus here is you should notice that what we just did here, or just as my like last little thought down here, is I took the derivative of our volume expression with respect to the radius, and what I got was the surface area of the sphere. This makes sense to me because if a sphere is growing, I'm asking how does volume change as radius changes? Well, how it should change is I like to think about this as sort of like paper mache, right? If you have like a sphere and you're just like adding on one more infinitely thin layer, how does the volume change with an infinitely small change in radius? Well, it's going to change by one computation of surface area. It's like you putting one infinitely thin shell onto the outside of the sphere over and over and over again. And so this is a generic relationship that we'll always see with integration, which is that integrals take in information about the edge and they tell you what's contained on the inside. Derivatives take in information about what's contained on the inside, volume, and they tell you what's on the edge. And the fact that I can say that in such layman's terms is really exciting to me, that this is just this generic property of 3D objects or even 2D objects here in calculus, that volume or that integrals take in edge information. And honestly, I mean, edge, it's like the left bound, the right bound, the curve that bounds the whole thing. It's all the edge information is what integrals take in, and integrals tell you what's contained by all those edges. Derivatives take in a contained item of volume, and it tells you what does the edge look like right there. So a super satisfying kind of verbal description about what are integrals and derivatives doing. And this is generally true, that you should be able to take any volume formula, take its derivative, and land at a surface area formula, which is really cool right there. So other highly satisfying things. And I think these are just so great because it's like the first time any of us ever see these formulas is usually like something like 8th grade. And then I just love that there's still things to find out about these, in a sense, simple formulas, even when you're now like in Calc 2, and that will continue to be the case. So that this idea that I'm throwing at you right now is like one of the culminating ideas of the end of the Calc 3 semester out there. It's like this is still like sort of a deep concept. This isn't just some formula, right? Deep relationships between these things. Super cool. Okay, so there's our first one right there. We just got our first volume right there. We did it by integrating an area formula. The last thing I want to say before I walk away from this problem is don't be afraid to write word integrals. I don't think that you think that we're actually going to do integration at this line right here, but this is helping me get stuff on paper so that I can stop and break down the problem into pieces. I can see based on the picture that this was going to be a dx integral, so I want to pass through all the different x values of interest, negative r to r, it's a dx integral. I'm putting my pieces together right here. This allowed me to stop and think about what does my area expression look like as a separate idea, rather than me just being here like, imagine if you just tried to just blurt out this integral line right here, the one that we actually worked from. I don't know how you're supposed to get to this right away. So like, be comfortable with word integrals, and then be comfortable with writing non-doable integrals because they've got the wrong variables in here. You're going step by step. It's like a light improvement every step of the way. Trying to just be there where you need to be is hard. You need to take individual steps to get to those places. So do a lot of like writing down what you know so far. There's nothing wrong with that. I will never assume that you think that these first two integral statements are super useful to us, but by doing a little bit more math, we've turned them into something useful. Everything should be this step-by-step process, a little bit more of a story rather than you just knowing some formula. This isn't about knowing formulas anymore. This is now more about smart construction, and construction happens piece by piece, right? So get comfortable writing these slightly weirder integrals up top right here. I think it's really beneficial. I did a lot of it last video with our red upper and blue lower and stuff like that. Use more words. I feel like I use more words in calculus than like anybody else I ever see, and I don't know why they don't. Describe things to yourself. It doesn't have to be a perfect algebraic formulation all the time. Cool. Let's hit another example here. One of our main topics here that we're going to see, and this is going to closely relate to the cylindrical shell method that we're also going to see as our first video next week, is that as we rotate a two-dimensional shape about an axis, this is a very typical thing to want to do here. What we're going to see is that we're going to be able to break down our Riemann objects as disks or washers. Where when I say a washer, I mean like a disk with like a hole punched out in the middle. And you should recognize that we just did this up above, right? What we added up was a bunch of Riemann disks. I said that our Riemann object was a circle, and that's like a disk, right? Well, actually, technically speaking, this is a disk and not a circle. A circle is the edge. It's the points that are at the same distance from a center. A disk is like the solid object right there, technically speaking. So we sort of just did a disk method up above, but we're going to do something that's a little bit more formally a disk method for this guy right here. So this is number 4, by the way, from the homework problems in section 6.2. And let's go ahead and find the volume of the solid that you get when you rotate some region about the x-axis right here. We're going to want to obviously describe the region a little bit better, but what we're going to do is we're going to take just a root function right here, and we're going to place it in a normal 2D grid, but then we're going to take the x-axis and we're going to spin the x-axis all the way around, and it's going to sweep out a volume as it spins around right there. So the volume that we're creating here is created by a rotation of an axis right here. So let's take a look and see what this shape looks like. First things first, obviously I kind of have to be able to graph y equals square root of x minus 1. So I'm thinking to myself, this should be like the graph of y equals square root of x, shifted right 1. And by the way, I know this graph only exists in the first quadrant and we're shifting it right by 1. All my values here are positive, so I feel pretty reasonable about kind of just drawing a first quadrant graph right here. And so I've got a root function that's on the x-axis here. And what we are thinking to ourselves is that since we shifted right by 1, this function now starts at x equals 1. We are interested in the region between x equals 2 and x equals 5. There we go. So here is our region of interest. This is our two-dimensional region of interest. And what we are going to do is we are going to rotate about the x-axis. So by the way, this little symbol right here is our indicator that the x-axis is what's experiencing the rotation right there. You should do these to help yourself. You'll see the book make those little like rotation symbols right there on an axis right there, indicating that we're kind of talking about the volume that's created by doing this, right? So kind of what you should be picturing for yourself right here is that without this restriction of 2 to 5, right, if we're picturing this entire root function, we're sort of building a sideways cup right here with this revolution. It's just that we're going to lop off this one little tip right here, and we're not going to go into an infinitely deep cup out there. We're just getting one slice of like this sideways sitting cup that we're experiencing right there. The important thing then to me is that we are going to be able to describe this in terms of circles again, right? The thing to notice is that since we are rotating this shape around the x-axis, the distance that this curve stays from the x-axis is constant. This curve, regardless of what part of the rotation that we've gone through so far, is always exactly square root of x minus 1 units away from the x-axis. The definition of a circle is it's the set of all points that are a constant distance from a point at the center right there. So what we're going to get when we rotate this thing is something that we could describe with slices that are all circles, which is pretty dang nice again there, right? So this circle shape is going to continue to be involved. Anytime there's rotation, circles are involved, and that's going to be very useful for us in the description that we're trying to make right here. All right, so our object that we're creating then, our one Riemann object, is going to be like one of these circles right here, right? I'll redraw that circle. This is my Riemann object. And I should use my slightly more appropriate word, the disk right there, because it's filled in, right? It's got area. And what we need to be able to describe is, again, we need to know what its radius is right there. If I can get the area of one disk, then I can add up all those areas for each of the appropriate x values and arrive at an overall volume right here. So what we need to be able to describe now is, what is this R right here? It looks like in this case, I think that we can just say that R is Y, right? It is just the height from the axis to the edge of the curve that we're looking at. This one's not too crazy. In a minute, when we go to talk about things like washers and disks rotated around not just the X or Y axis, we're going to get things that are slightly more complicated than this. But measuring from an axis means that we're usually not doing anything too weird. The X or the Y axis, we're measuring from 0. So we're just getting the height that it is. So it seems like square root of x minus 1 is just what our radius is. Right? So it seems to me then that the area of this disk And I say general disk because I don't want you guys to think that this is like particularly the disk at x equals 3 or something. I'm always trying to draw a generic Riemann object that is representative of potentially any one of the infinite number of disks that are out there. I'm not picking out one, I'm making a general representative. And that's why I'm using x's and y's instead of like the number 3, stuff like that. So the area of this general disk then should be, area is pi r squared, which is really pi times square root of x minus 1 squared, which is really just going to be pi times x minus 1. So it looks like that is the area of our representative Riemann object. And all I have to do now is integrate over and notice here we built again a vertical disk in this case. So I'm just going to accumulate all of my vertical disks from x equals 2 to x equals 5, and we'll have ourselves a volume here. So staying my kind of, I don't know, if you guys don't write this line, I'm cool with that. But like, I'm trying to be a little bit more formal here with this. So I'm integrating my area function in terms of x, dx, from 2 to 5 right there. And again, notice that we could have just said that this was pi y squared. That would be a sub y, right? We wanted this in terms of x, and it became this guy right there from just doing our substitution for our function right there. Right? Nice and easy. So this one should be pretty easy. Again, the setup's the hard part here. There's going to be plenty of times this semester where I'm just going to say to you guys, oh, just set up the integral. Don't do the integration. One of the major keys to this class is learning how to do integration, but some of the other stuff in this class is way more about, can you even describe the quantity of interest as an integral? Knowing that potentially we could go look up the integral or something like that. Building integrals in this class, I think, is a little bit more exciting than actually doing the integration itself overall. And so that's just building them is enough of a challenge here typically. So pretty easy integral here. Not going to get a lot easier than this. Again, I'm going to continue to encourage you guys to do the x equals there, even though you technically don't need, like, I don't know, a lot of people just write 2 and 5 instead of x equals right there. Just keep remembering that we have so many variables of interest, kind of like, and for the rest of your life, like how many one variable scenarios do you honestly think you're going to find yourself in? Like, just not that many. Be explicit. Don't confuse yourself. We could easily end up accidentally thinking Y stuff when we mean X stuff. We've got R's that are going to be floating all over the place. In fact, we're about to have even more than one R term in our next example right here. Do yourself a favor. I'm not saying do this for me. I'm saying do it for you. It just prevents you from making stupid mistakes that are not concept errors, they're execution errors. Execution errors are the dumb errors of life. If you know what you're doing, do it right, and do it right by keeping track of things. It's just good bookkeeping. So what do we get here? 1/2 times 25 minus 5 minus 1/2 times 4 minus 2. 12.5, let's see here. 12.5 minus 5 is 7.5 minus, and that's 2 minus 2, well, that's 0. So 7.5 pi or 15 pi halves. Pretty easy integration right there, 15 pi halves. So we've now got our volume of this region that was obtained by rotating a two-dimensional shape about an axis. The best thing about rotation is rotation makes circles. Circles have easy area descriptions, and so therefore it makes it pretty easy for us to make volume descriptions because we're just integrating the area. I think in both of these cases, the biggest challenge is you saying, what do I want my Riemann object to be? And how do I describe the area of that Riemann object? The integration in both of these cases has been pretty easy. I don't think I have anything else to say about this one. Keep thinking about Riemann objects. What's the one-dimensional lower object that you want to add up a bunch of, and what's the smart way to do it? In this case right now, also, by the way, see, we had infinite symmetry. There's literally any symmetry that you could ever want with a sphere, so we could have made any dx, dy, whatever choice we wanted, everything would have worked out the same. Here, there weren't a lot of other better choices. If you were to think about trying to do this like top down in a sense for this volume, that our shapes would have been, I don't even know what these shapes would really look like right there. And that's a problem. If I don't know what the shape looks like, how do I describe its area? So in this one, I think this one's easier in the sense that there's only one natural choice for the Riemann object right there. So it's a little bit harder. Like you don't have to be like, how should I build this? Like we did rotation. Rotation makes circles. Circles are your friend. Pick your Riemann objects that you're easily just adding up a stack of circles. That's pretty easy right there. So now let's mix it up a little bit. The reason why the last one was so easy is because our radius was really just literally the function that we were given. That was like the boring part of this guy right here. We didn't have to think hard about what our radius was going to be. This guy over here, we're going to have to think a little bit more carefully about how to state what our, and again, it seems like we're again going to rotate about an axis. Rotation, as soon as you see that rotation is a part of it, you should be thinking, all right, where's my circles at? Always. So we're going to be looking for circle area, but since we're going to rotate not about the x or y axis, but about the line y equals 4, it's going to be a little bit stranger as to how we define what our radius is going to be. And not stranger, it's just, we just got to be a little bit more careful here. So what's this thing look like? So we're rotating the region bounded by two curves. So these are our boundaries, y equals x squared and y equals 4. Then we're going to take that two-dimensional object and we're going to rotate it around y equals 4. So what this looks like to me then is, got my parabola here, there's y equals x squared. It's going to be bounded by the line y equals, curve, y equals x squared, drew that. It's going to be bounded by the curve y equals 4. Here's my y equals 4. So this is our region of interest now. It's bounded by y equals x squared and y equals 4. And what we want to then do is go ahead and rotate around that y equals 4 axis right there. So what we can kind of see is we're getting this weird sort of like a lemon shape, right? This isn't like a sphere because it's going to have these like sort of pointy corners on the ends right there. I think a lemon is a pretty reasonable description, or at least I should say when I draw my by hand drawing, they end up looking like lemons. Maybe that's my more appropriate thing to say. So we want to ask ourselves in this case now, maybe it's a little bit less clear as to what we're actually going to get from our rotation right here. And so I'm going to propose two different ways that we can set this up, and we'll ask ourselves which one we think is better. So Okay, that was too low. That's not y equals x squared right there. I can give myself a little bit more parabolic action here. Um, right there's our y equals 4 line, and then there's going to be the top half of that parabola. Since we've rotated the parabola around, it's going to have that parabolic shape both on top and on bottom right there. And so I want to think about doing this two different ways, right? So one thing, if I were to do this as perhaps I'm thinking to myself, maybe I want to do a dy integral here, where I want to accumulate one sheet for each of the heights that we end up experiencing out there. If that were going to be the case, then we would need to come up with a representative circle here and a representative circle here. And one of the things that I'm seeing is that this curve and this curve aren't defined necessarily by the same equation, right? This is my y equals x squared. What function even is this? Stop and take a second. What function is this parabola? Well, I'm thinking that since it was mirror over the line y equals 4, the vertex, which started at 0, 0, should now be up here at 0, 8. And it should be opening down because it's been flipped over the y-axis, right? So I'm thinking that this right here is the curve y equals 8 minus x squared. Not too terrible to think. We've flipped the parabola over the line y equals 4 right there. So I feel like if I was going to do a dy integral, that I could do something like a 0 to 8, somehow get my areas in terms of y, dy, but that feels like it's going to be clunky to me because we've really got two different y's that we're trying to describe right there. So we really might need to be doing like a 0 to 4 and then 4 to 8 to get our circles out there. And immediately that reeks to me of our problems that we ran into in 6.1, where now we're like breaking things up over several different subdivisions. And I'm immediately thinking to myself, I don't know, do I maybe want to do this like a little bit different of a way right here? And so maybe we could think about doing the same type of thing, but a dx integral here. In this case right here, we could think to ourselves about this disk being our Riemann disk, which kind of makes sense because it's that's the direct, like we rotated around this axis right here, right? So I think our natural circle to build is perpendicular to the axis of rotation. I think that seems a little bit more natural to me. In this case right here, and by the way, if that's at a height of 4, that's going to be going from -2 to 2 right there, since our height is at 4. So it seems to me like this guy is going to have, and again, if I'm doing a dx integral, this means to me I'm going from left to right, which is why I wanted to start identifying this guy right here. So it seems like we could go from -2 to 2 of some area expression in terms of x dx right here instead. I think that's going to work out for me. I think maybe a little bit nicer because I can see that there's only one representative circle that I need to be able to describe to move across this thing right there. So like maybe this is like a little bit more natural for me right here. And we still are, bounded above and below by y equals 0 and y equals 8, but that's not really how I'm describing this one. I'm describing this in terms of its x boundaries rather than its y boundaries right here. So what we still would need to describe then is what is this radius going to be, right? That's kind of always all three problems today has been like, wait a minute, how do we describe the actual quantities of interest? I want to get my area stuff in terms of the x location here. And it seems like that's going to be describing, I want to get a radius term right here so that I can compute my a of x. So what's this going to look like right here? Well, how long is this length? So here's kind of the way that I like to think about this. We're going to go from y equals 0 to y equals 4. And that's a total length of 4 there, right? What I can see we're going to end up with right here is that some of this chunk is going to be r, whereas another piece of this chunk is going to be like that y equals x squared piece, right? The height, so watch right here. The height from the x-axis up to the curve, that height is the height x squared. The overall height is 4. Therefore, 4 minus x squared leaves me with the radius that I want. All right, so again, stop and think about just the 2D picture. The height from the x-axis to the curve is y, also known as x squared in this case. The overall height of the bounding line is 4. We want the height from the curve up to 4, just this part. So let's take all of the height 4 and subtract off the part we don't care about, the x squared part, and what will be left over is the radius of these circles that we are accumulating as our Riemann object from left to right there. So this is good to me. I feel like I've got a radius term, and if I've got a radius term and I'm adding up areas of circles, that's really easy. So I think we can go ahead and kind of flop this guy inside of an integral now and see what we have. So this says to me then that my volume expression should be an integral from -2 to 2 of my area, which I think is going to be pi times r squared. There's pi r squared. Got it right there. Now, I do want to point out one maybe it's a little bit nicer thing that we can also do for ourselves right here. One of the things that I told you guys, I think in one of our videos last week, was there was at the end of section 5.4 or 5.5, something like that, the book discussed some symmetries, and I'm kind of seeing one of those right there. It's pretty obvious to me that the left-hand side of this is exactly the same thing as the right-hand side of this thing right here. I can tell that I have an even function in my integrand and symmetric bounds of integration over 0. So I think that it's okay for me to rewrite this thing. So one thing I'm going to do is I'm going to pull the pi out front, but another thing I'm going to do is I'm going to double the integral, but only integrate from 0 to 2. This is just saying only find the right half of your volume and then double it to get the overall volume, since this object is left-right symmetric. This will just make our evaluation ever so slightly easier. And now we're good to go. Now we've just got some easy polynomial integration to do here. All right, so it looks like I'm going to go ahead and follow the general lesson of do as much algebra as you can before you start integrating. I'm going to expand this thing. 16 minus 8x squared plus x to the 4th. And let's go ahead and integrate it. And I'm going to be getting here 16x minus 8/3, bummer, x cubed plus 1/5 x to the 5th, evaluated from x equals 0 to x equals 2. I hope that right now you're saying to yourself, oh man, good call on getting rid of the -2 as one of our bounds. It helps use these symmetry things to just simplify your math quite a bit here. Since this was a polynomial, there's an x in every term of the integral of a polynomial. So when you evaluate at 0, it just goes to 0. So this just says literally just plug in 2 and we're done. Uh, 2 cubed is 8, so that's going to be a 64/3. 2 to the 5th is 32, so that'll be a 32/5. And I'm gonna do the lame thing and just reference my notes. All we're doing is adding fractions right here. I hope that nobody's surprised by this. And so, in fact, I'm just gonna write our answer right here. I'm just doing some fraction math. There's nothing exciting that's happening right here. Add some fractions together. You will find this to be 5/12 pi over 15, that common denominator that we can see there at 15. So just doing a little bit of fraction math right there. 512 pi over 15 is going to be our final volume for this shape that we've arrived at right there. All right. So I think that the most important thing, sorry, moving away really quick right here. I think that the most important thing to be taking away from this problem right here was that we had to be a little bit smarter about building our radius pieces right here. But again, mark lengths that you know, again, this is just good bookkeeping is all that we really had to do to be able to build these parts right here. The total height from the axis to the bounding line was 4. We wanted one piece of it, and so we subtracted off the piece we didn't want from 4. So a very, very common thing to see in a lot of these volume expressions right here is whatever the height or width is of the axis of rotation. It's very, very common to have expressions that include exactly that. The location of the axis of rotation minus the function. It's not always set up that way, but this is a pretty typical thing, and you'll see several of these in the homework and stuff that are going to be phrased kind of exactly like this. Axis of rotation was y equals 4, so this was really like a y quantity minus a y quantity right there is what we got for an overall height. It should be some measure of height, and we did one of our heights, the overall height, minus the height we didn't want, keeps the height that we do want. So y total minus y to be discarded equals y to be kept, the radius right there. That was the height that we defined the radius to be. So expressions that look like this, pretty typical. The ay integral here as well. Let's see. So I think I could do the ay one. Let's see here. I do believe that we could like double the 0 to 4 one here. What would that look like? It seems like, yeah, if we wanted to do this guy the other way. Let's see. So looking at this guy here, a thing I'm thinking is that rather than actually having to do two integrals, we could just do the bottom half and then double it to keep the top half here. So I'm thinking that we should be able to build some integral from 0 to 4 dy. That's got some area in terms of the y value right there. So looking at these being our circles that we're adding up. And this circle right here, I've got to be able to determine this length as my radius right there. And so this is going to be starting at an x value of 0, and it's going to be going to the x value of, I think we could be saying x is square root of y. Right? Because I'm solving the equation y equals x squared for its opposite variable there, right? So maybe that's like my general overall statement that I should be making right there. The x distance from the x-axis to the boundary, that is exactly the radius of the circle I want to accumulate. I want to accumulate one of those circles from 0 up to 4, and I think I should double it. Let's see if this pans out to be the same. So this should be pi times r, which is square root of y, squared. Wait a minute. What? Yeah, pi times square root of y squared dy. Is that really going to give us that same thing? I don't think so here. What am I doing weird here? I don't feel like this is, I feel like I'm setting up something wrong here. What am I doing wrong? By the way. Why is that not the same thing? I guess what I'm thinking here is I don't think that these are circles. Right? I think what's happening here is that we're actually getting not circle shapes here, but actually like ellipse shapes in here. I don't think that this is a circle, and I think kind of the big takeaway with this is we want to build this Riemann circle to be perpendicular to the axis of rotation. That's how I know that I'm actually getting a circle out of this. I think that what's happening here is that as we rotate this parabolic shape right there, we're not taking a semicircle and rotating it around to get a sphere, right? We're taking some other shape. And so maybe now think about this. If we were taking like a V shape and rotating it around an axis, certainly we're not getting circles in this direction. And since we're not taking a semicircle here, we're not getting circles in that direction. So I think the reason why this is not correct is because that horizontal shape that we're getting, cross section, is not a circle here. So I think my answer to you is I don't know how to do it the other way because I don't know what this shape is. So, good question, Austin. And the answer is I don't think I can. And again, and it matters that we build objects that we actually know the shape of. Like if you can't compute the area of the two-dimensional object, then you can't accumulate it to get our three-dimensional object right there, right? So again, I feel like this looks like it's a semicircle down there just because I'm bad at drawing. But I think, like I said with my example, take this to a more extreme example. Imagine that it was like a shape that was like a V and we rotated it around. We're not going to be getting circles as our horizontal cross sections, but we still would be getting circles for our vertical cross sections right there. And so I think that a typical thing is when we're doing any type of rotation, the cross section that you want is always going to be perpendicular to the axis of rotation because that's always going to be guaranteed to be a circle. So I think the lesson here is circles are your friends. Circles come from being perpendicular to an axis of rotation, and so that's the one that we want to be doing right there. So this isn't correct because it wasn't a circle. And that's why we're not getting our same answers right there. So hopefully that's your satisfying, unsatisfying answer for that guy right there. That we chose the cross section in which we knew what the shape was of our two-dimensional cross section. Good question. Thank you for prompting me to do that since I sort of glossed over that for sure. I just wasn't thinking about it because I knew I was going to do the shape that I knew was a circle right there. Then I stopped thinking about the fact that that was not in fact a circle. So now let's do the one slightly harder version of this guy right here. The thing that's been easy about these previous two examples is that our shape of interest was butted up against the axis that was being rotated, right? Here's our shape, our 2D shape. It's touching the axis of rotation. 2D shape, touching the axis of rotation. So what that produced was just circles, right? 2D shape, touching the axis of rotation. Well, the rotation was already done there, but you could picture the x-axis being our axis of rotation to produce that circle. In our next example here, and by the way, is this our last example here? Let's look at one where our axis of rotation does not actually touch the shape that we're interested. Oh, okay, our shape does not completely have as an edge our axis of rotation here. So let's check out our washers here. So the difference between a disc and a washer is that a disc is solid, but a washer has a hole punched out in the middle. So it's sort of like a circle minus a smaller circle, right? As far as area goes right there. And that's exactly how we're going to make our area computation happen. So let's find the volume of the solid obtained by rotating the region bounded by these two curves, square root of x and just x, about the line x equals 2. So as with all these good things here, let's draw our picture first. I've got the square root of x. Oh, on the contrary, room with Google Eyes, I have an unlimited number of washers. They're just never the ones that I need, and I can't find them when I'm looking for them. You go look at the bottom of my toolbox. It's just like 76 Allen wrenches from 76 pieces of furniture, and the 80 washers that I somehow managed to never actually assemble onto them. I have unlimited unused washers. So I'm going to draw this like a little bit skewed right here just for the sake of visual emphasis. This isn't exactly like the x-axis one, maybe not. Actually, I don't know. Maybe that did actually work out really well right there. So some simple things right here is that without even doing any algebra, I know that these graphs intersect at 1, 1. That's just a really simple fact about simple functions that literally just have a single x in them right there. and you're not like adding or subtracting or multiplying or anything like that. We're clearly at 1, 1. So the volume of the solid obtained by rotating the region bounded by these two curves. So the region bounded by the two curves is this region right here. So that's our two-dimensional region of interest that we're rotating. But we're not, but like it's a slant region, right? It's in like an oblique region. It's not up against an axis of rotation. In this case here, our axis of rotation is this line that's out here at x equals 2. So we're rotating about the x equals 2 line right here. And so we're going to get this sort of odd shape. This is sort of like, you should now picture like a cup, but if you cut the base off of a cup, it's sort of like a floating piece of cylinder, but it's also not a cylinder. It's like a slant cylinder right there. So kind of a weird looking shape right here, right? So we're gonna get, as we rotate this thing, there's gonna be, sort of our other piece of it on the other side over here, right? So we're gonna get a solid. It is one piece that's generated by rotating this guy around that axis of 2. And man, again, it really matters that you stop and picture this. Like picture like a snow cone cup that's like a triangular. I don't even know my name for that. What's my whatever, a snow cone cup, and then chopping off the bottom. Except we actually have a little bit of thickness on the walls right there. This is actually like the shape of what this wall looks like right there. So we're rotating this object around, and what we can kind of see for ourselves here is that, now let's take the lessons that we just learned from the previous problem right there. Thank you for your good question, Austin. I know now that because I am rotating around a vertical axis, I would like to therefore be accumulating washers from top to bottom. I know that the circle that I will experience is going to be horizontal, and therefore I want to build those circles vertically, a stack of circles, or in our case, a stack of washers, but that's really, 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 really close to a circle, right? So my Riemann stick in this case right here is right here. There's my Riemann stick. That's the stick of which, if you rotate that one stick around, it's going to give you one single washer, and we're going to add up a stack of washers that are all infinitely thin to get a volume of a solid here. Right. Let's see here. We're going to need to define some radii is one of the things that I'm kind of noticing here. So again, this thing's getting rotated around this axis. So I'm drawing these bars in reference to our Riemann stick that I just drew right there. Our Riemann stick is getting rotated around this axis to form a washer, right? It's a circle with a circle cut out from it. And I'm going to just call this guy right here a lowercase r for our inner radius of our washer, and I'm going to call this guy capital R for our outer radius of our washer. A washer is a circle with a circle punched out, and so I want to know where the washer sort of starts and where it ends, right? The inner radius and the outer radius of that washer. That's right there. Hopefully you're on board with the fact that we're going to want to describe these two R terms in terms of like X and Y and stuff. But let's get some setup first. Again, I think doing some like word stuff and drawing some more pictures is still more useful right now before we go hop into our actual integral here. So I'm picturing that we're taking this Riemann stick right here, and we are rotating it about this axis. And what that is producing for us is it's going to produce for us a washer. Where this, so the problem with me drawing this picture now is that this Riemann stick and this washer are not being viewed from the same perspective. This is like my front forward view of the Riemann stick, but this is actually my top down view. Simply because if I were to draw to you guys this washer laying down, it would actually look like a rectangle from the side. Right? Do I have a, I mean, that's just an example of this right here. We know that this cup is a cylinder, but if you just look at its two-dimensional projection, this is actually just like a rectangle. Right? And that's, so from the side, this would just look like a stick again. So that's why I'm drawing it this way right here. So maybe a thing I can do to help us is to indicate that that axis of rotation is that central part right there, and that the Riemann stick itself is the thing that was rotated around to produce that guy right there. So I'm just going to say, should be laying down. So how do we get the area of a disk then? Or sorry, area of a washer. So again, our outer radius to the very edge is what I'm calling capital R. Our inner radius to sort of where the washer's area begins, I'm calling lowercase r. So it seems like what we could do to get our area is find the overall outer area, pi r squared, the actual whole disk, but then subtract off the missing chunk from the center. By the way, be careful that you do not suggest that this is capital R minus little r squared. It is individually squaring each of those two radii and then taking their difference. I definitely have some people do like r minus r squared, and that's not correct. So don't make that same little algebra mistake right there. It is one area of a circle, the big circle, minus the area of the inner circle, the missing part that we've got going on right there. So what this sort of means to me is like I know what my integral is going to look like right now. I can tell that we're going to stack up washers vertically from bottom to top. I know that this is going to go from a height from 0 to 1. So I know that my volume is going to look like the integral from 0 to 1 of our, and I'm just going to say here, washer area. It looks like I'm doing a dy. I'm doing a vertical stack right there. Y is the infinitely thin cross section. And I even know kind of what this looks like. This is going to be pi capital R squared minus pi times lowercase r squared, the outer radius minus the inner radius. So it looks like we need r and r in terms of y. So now let's revisit our diagram, revisit our equations, and see if we can work this out. And again, don't feel like you have to figure out the whole thing to write down an integral. Look at the first two integrals that I wrote and recognize that they're crazy generic, but that they're right. I don't have all the details I need in them, but I haven't written anything wrong so far. I just haven't written anything that I can actually like integrate yet, and that's okay. I'm working towards this piece by piece. I'm thinking procedurally through this rather than expecting that I'm ever just going to be able to blurt something out. Your blurting out ability is just not going to be a thing for the rest of the math that you ever do for the rest of your life. So help yourself. Make everything be a step-by-step process rather than trying to do everything in one big whack. So we need this r and r, and we need it in terms of y. Well, here's the things I'm seeing. We are clearly measuring this radius as an x length. It is being measured horizontally. So I think it's easier for us to describe r in terms of x. And the good news is that we have equations that help then relate x to y. So I am thinking to myself, it looks like, what is our little r going to be? Well, if I am at this location that's right here, if I am at this location right here, I want to know what is this length of r? It looks like this length of r right here to me is 2 minus x sub r. And I'll say the x of that little radius right there, right? It's the entire length 2, which is from 0 to 2. But what we want to chop off is the x distance associated with that little radius right there. And that really means to me is part of my linear one right there. It looks like my capital R, similarly, is the entire length 2, but I want to chop off a little bit of x, the x that's associated with that square root x right there, right? And the good news is that I have ways to solve for both of these parts right here. It looks like the x value for the linear equation is literally y. So x is y. So I think for lowercase r, I can describe this as just 2 minus y, because the x associated with this equation is the same thing as y. On the other hand, this x value right here seems like it should be y squared, because if I squared both sides of the square root equation, I could get my x expression right here as being the same thing as y squared. And so I think this is going to allow me to make the two statements then, that r equals 2 minus y, and that capital R is 2 minus y squared right there. Right? So again, I'm measuring the entire length of 2, and I'm subtracting off the x value associated with the linear equation for the inner edge. The linear equation was y equals x. So when I say 2 minus x, that's equivalent to 2 minus y on the line. When I do 2 minus the x value associated with the curve, that's really 2 minus the x that's associated with this equation. And in this equation, if we solve for x, x is the same thing as y squared. So this capital R length right here should be all of 2 minus the y squared length that goes from the y-axis to the curve. So 2 minus y squared is going to be our capital R length that we've got right there. And using these two guys, we can now I'm going to just draw myself a nice arrow right here. So I think we now have a volume expression, right? So in terms of this washer, I know this is a washer problem because my axis of rotation is not touching my two-dimensional region of interest, meaning that there's always going to be this gap between our actual object and the axis of rotation. And so that's going to result in a Riemann object always being a washer with a missing chunk in the middle, not just a disk. So instead of just pi r squared, it's pi times the outer radius squared minus pi times the inner radius squared. It's still just area is what's being integrated. We just have a slightly more complicated area expression. It's just the area of a washer instead of the area of a disk. Nothing too much more crazy there. So I think I can now write this as 0 to 1 of pi times, we just decided what was capital R. We decided that capital R is the same thing as 2 minus y squared. We're chopping off the inner part of our disk, or our washers that isn't there, the hollow part in the center. So this should just be our pi times, and again, what did we decide that little r was going to be? We decided that little r was just 2 minus y because y is the same thing as x on the straight line part. And the straight line part is always the inner part of our washer in this case here. And now we have ourselves a nice integral that represents the volume that we get by rotating that two-dimensional object around that axis x equals 2. Let's do it. We, again, just got a bunch of polynomial parts here, so how bad could this be? I'm certainly going to factor that pi to sit out up front right there. Make things a little bit easier here. I'm going to square out both these expressions here. I'm going to get a 4 minus 4y squared plus y to the 4th. Be careful, by the way, all of your washer method stuff, very common thing. People kind of screw up with this negative here, forget to distribute it to this entire quantity here. So I'm going to make sure I use some parentheses. What do we got here? 4 minus 4, gone. It looks like we will get some y squared stuff, some y to the 4th stuff, and some y stuff. Looks like we'll get some grouped up y squareds there. So let's rewrite this as a more typically visualized polynomial and then integrate here. So it looks like I have only a single y to the 4th. It looks like I have negative 4y squareds and then another negative y squared. Again, don't forget to distribute right here. So negative 5y squared. And then finally getting a positive 4y because we're distributing that negative. So let me shake my fist at Microsoft Word right now to give me, yeah, that's right. Good job, Microsoft Word. Good for you. All right, let's do the dang thing. Look at those nice bounds of integration too. So I'm hoping that you guys are just on it by now for your your integrals, especially polynomials, getting all your your coefficients dealt with out there. Best bounds of integration for any polynomial integral that there could possibly be. 0 to 1 is your best friend. When we plug in 0, everything goes to 0. I don't even need to think about that one. When we plug in 1, we're just keeping all of our coefficients. And if we do, I think I can at least do this little bit right here. We're going to get 3/15 minus 25/15 plus 30/15. And that gives me 5 plus 3 is 8/15. So disks and washers, those are the two Riemann objects that are always going to be natural to construct whenever you are looking at a volume of revolution. Whenever we rotate about an axis, there's always going to be a circle or washer that has been created, a two-dimensional object that you can stack up an infinite number of, whether it's left to right or top to bottom, to accumulate a known area. In this case, we have like sort of slightly less options, but what we're going to see in the next one up here in section 6.3 when we go to cylindrical shells is that we're going to see scenarios where it's like, can I describe it this way or can't I? And we're going to get back to sort of this like strategy of determining how can we identify what those volumes are going to look like here. So I do want to point out there are some other ones that the book does here. I would encourage you guys when you're looking at the examples in the book does go through a few other examples of shapes that are not based on areas being circles and washers here, where there's some like square ones. Okay, great description, Austin. I needed something there. The shape that we integrated was sort of like a volcano with its top and magma top with a blown off top and the magma chamber emptied. Yeah, it's like a hollow mountain in a sense out there where it's yes. I was just looking the other day at some comparison pictures of Mount St. Helens before and after, and it's like you can actually still see most of the walls, and then it's just immediately that crater down into the center right there, with then just like a little bit of a peak that's like hidden on the inside now. Super cool looking. Yeah, and I should also say to you, I'm glad that these are the things that you're thinking about right now, because if you can't visualize this three-dimensional shape, then you're in a kind of a tough shape right here, right? Like kind of getting your 3D visualization down is a pretty important thing to be able to do here. And so think about those types of things. Having a good description for yourself of what these shapes look like, and remembering that rotation is always going to give you something that is in some sense circular, and therefore can be described by circles that are perpendicular to the axis of rotation, is really our key for this. And so, yeah, so as I was saying in the book does do a couple other examples that are pretty important of area expressions that are not just circles and washers. I think I did those ones here today because I think those are the ones that are a bit harder to visualize. But the book also does ones where they show some like pyramid shapes that are made up where your cross-sectional area is a square. And that could make sense. So never forget that our most generic thing that we did today was really just saying we want the integral of area, dx or dy, to compute volume. We did that in every single example that we did today. Whether you're talking circles, disks, washers, whatever, is irrelevant. It happened today that the examples that I selected kept on having to do with pi r squared, but it's completely reasonable that the areas that you are accumulating are not necessarily circular. Those just arrive from rotation, and we're going to talk a lot about some rotational things coming up here, so I stuck with those. But do make sure that you've looked in the book at some of the examples that deal with non-circle Riemann objects. The concept is exactly the same. Just look at it and say, oh yeah, I could see that we're just adding up those described areas there as well. On our written homework associated with week 2, I will ask you guys to do at least one volume problem that is not based on rotation. That is going to be based on a different area of an object right there. It's nothing too crazy. It's still going to be the integral of an area expression. You've got to decide bounds. You've got to decide how to describe that area. It's not going to be that bad right there. So that's all I've got here for us today. I feel like that went reasonably well. I appreciated the questions in there, keeping me on point with those things. I didn't make 40 mistakes like I made in the video yesterday, so I also feel good about that. I don't know, you guys call me out. Maybe I made some mistakes today, maybe I didn't. But I think we did pretty good here with getting our first volumes, extending our idea about what integration actually does for us. And I want, and really like our big takeaway here is like, you know, think in our most generic terms. I think that seeing that these three ideas right here make sense to you, even though we hadn't done this before and you guys still won't do this for another semester, I still expect that this just straight up makes sense to you as a formulation. Do I think that you can actually do the integration for this? No, you'll learn how to do that next semester. But the formulation of this multiple integral should still kind of make sense to you, that we can first add up in one direction to get sheets, then take our sheets and add those up in another direction to get areas. It's just how integration works. It's an accumulation of objects of n minus one dimension to get to n dimensional objects out there. So that wraps it up for me for today. Next week we're going to hit some more volume topics there. And what is it? We're doing next week. We're doing 6.3, and we're doing 6.3 is one of our volume applications. Oh, and then we get work. Work is a good one. We're going to get our first physics section next week. So work. There's some other things that go with the work section in there as well. But we'll get another sort of geometry section for our first video next week, and then some like physics applications as our other topic for next week. So I'll be seeing you guys for that. Have a good one, everybody.